Okay, so you may wonder what the words top and tot have to do with the binomial theorem, or Pascal's triangle, or any such thing that we've been studying. Well, what we're going to do is we're going to try to figure out the number of ways that we could arrange the letters for top and tot, and this will actually have bearing on the binomial theorem. So if you looked at the word top, it has three letters, and we can arrange those in different ways. Okay, we could keep the T in the front, but we could switch the P and the O, and we don't get a word, but we do get an arrangement of letters, three-letter uh, code or something, but it's not a word, but it is an arrangement of those three letters, and it's distinct from the first one. Well, if we want other arrangements, we've exhausted what we can do with T in the first spot. So let's get rid of that, and let's move the the O into the first spot, since that's the second letter. Well, we could have OTP, which is not a word, but it is it could symbolize something, or we could have OPT, which happens to be a word, but the point is it's a three-letter combination. Now we've exhausted all of the possibilities of having the O in front, right? So the only thing left to put in front is the P, and we could have PTO, or we could have POT. Okay, so some of these things actually happen to be words, but they're all, it looks like we have 6 different ways to arrange these letters, right? Now we could have counted that because there were 3 ways to put in the first letter, and then once you picked one of the 3 letters to be the first letter, there were only 2 options left for the second letter, and then 1 final option, giving us a total of 6. Okay, so notice that's 3 factorial is equal to 6. Now, when 2 of the letters are the same, our options are more limited. Now, if these T's are different from one another, we could still get 6 answers, but those T's look exactly the same. So we could have if I wrote TTO, that would be different than what we had before. And so far, the 2 examples that we have don't have O in the front, so we could put O in the front and then have T. But switching those 2 T's in the second and third position wouldn't give us another combination. So we really only have 3 ways to write this out. Okay. Now, how might we get those 3 ways? Okay. So it looks like we should be able to move things around 6 ways with a 3 factorial. If these 2 T's were different from each other, let's say that one of them has a red line or a red check mark next to it, then we could switch the 2 T's around and we could have a TOT again, but this time the red check mark would be in the front. And we could do the same thing for every combination that we have, and we would go from 3 to having 6 combinations again. All right. So how do we figure out the number of possibilities? Well, we take the number of elements in the set or members of the set, and we need to divide, though, by the number of things that are the same. Okay, since the 2 T's, we would get 6 things if the T's are different, but since they're the same, we have to divide by the number of T's that we have. So we have to put a 2 factorial here, and that will give us 3 times 2 factorial over 2 factorial, and only leave 3 options left. So we have to divide out what is the same. Okay, so it gives us half as many options as we would have had before. Now, what does this have to do with a binomial expansion? Okay, let's consider what happens if I were to take A plus B and cube it. All right. We could think of A plus B as being sort of a hat with a, an A marble and a B marble in it. All right. And we would have, if we're going to cube it, we have 3 such hats in a row. Now, what are the ways that we could pick out marbles? Well, we could pick 3 A marbles. All right. Now, using the logic that we were talking about with top and tot, we could think of how many different ways we could arrange 3 A's. All right. And the answer is there's only one way to arrange these 3 A's. All right. Now, we could have selected an A an A and a B. But what if we picked a B from the second hat or a B from the third hat? So it looks like there are three ways to pick two A's and a B. Okay, so this would correspond, obviously, or hopefully this is obvious, this would correspond to three ways to get our A squared B term, which is why we have a 3 A squared B, whereas this first thing would represent our A cubed term, and there's only one way to do that, all right? Now, if we go picking out of the hat again, we could pick an A followed by two B's. But we could have also gotten one A and two B's by saying B, A, B, or B, B, A. So those are all ways that we could get pull out one A and two B's. So notice again, there are three ways to do that. So this is, switching colors, 3A, B squares, all right? Then if we look at the last possibility, the only thing we haven't done yet is drawn all B's. Okay, now once again, there's only one way to get all B's. All right, so that would represent the B cubed term. There's only one way to do that. So the coefficients that end up in front of the terms when we expand are really ways of counting. All right. Now, there are three things in every one of these sets. The first one has, if we call these set 1, 2, 3, and 4, they all have three elements, but in one case, or two of the cases, they're all the same, and in the other cases, you have two of one and one of the other, right? Now, notice how this lines up very nicely with C 3, 1, okay? If we have three things, and we were to select one of them, okay, this would, I need to make sure I get this the right way. I'm sorry, this is like, let's pretend we're choosing A's. So we have three things and we're choosing all A's. So we've selected three A's out of three things, all right? So what do we end up with that? That's equal to 3 factorial over 3 factorial over 0 factorial, which is just equal to 1. Well, that's exactly how many ways we were able to arrange the set of all A's. If we look at AAB, or having one B, okay, we had a combination of three things and we only took two A's for the three things, right? So this is comparable to 3 factorial over, if I look at that, that's 2 factorial over times 1 factorial. Okay, so because there are a pair of A's, it divides 3 factorial by 2 factorial, and we end up with 3 times 2, I'm sorry, if we expand this, it would be 3 times 2 factorial, basically over 2 factorial, which is 3, right? Now, if we keep going, this would be three things, but we only have one A this time. And the last one would be, we have three things and we're choosing 0 A's. So if we look at that, that would be 3 factorial over 1 factorial, 2 factorial. Well, we can see that's exactly going to give us the same answer as the previous column. And choosing 1A means we have in fact chosen 2 B's. So the math ends up being symmetric. And choosing 0 A's is the same as choosing all B's. So we end up with 3 factorial over 0 factorial, 3 factorial, which is exactly identical to the first set of options. So we could have expressed the coefficients in terms of combinations, right? Let's see how this would play out if we had 4 things. Okay, let's consider if we had A plus B to the 4th power. We'll go right to that. Okay, so if I have A plus B to the 4th power, I know that I'm going to get, well, let me write it out, A plus B times A plus B times A plus B. It's like having 4 hats with balls that are labeled A and B in each one. It is possible to get all A's. Now, like before, we would expect there's one way to get all A's, right? Now, if I were to pick 3 A's and a B, that would be like A cubed B. That would be comparable in terms of combinations of having A, B, A. It's kind of like with cards, it's like you have the same hand of cards. You're not worried about whether you got the B last or second. Actually, I should have put it in the third spot, so I'll do that now. And then finally, I could have a B in the first spot. Okay, so there were 4 ways to do this. Now, what about A, B, B? Okay, so you could pick 2 A's and then pick 2 B's, but we could move this around and we could have had there should be 6 ways to do this, A, B, A, B. Let's see if I can get all 6. Let's stick with A, B, B, A. Okay, so we switch that around. And we don't yet have a B in the first spot. We could have B, A, B, B, A, B, A, and B, B, A, A. I believe those are all 6 ways of doing this. Then we move on to the A, 3 B's. Okay, and I think you can believe that's the opposite of doing 3 A's and 1 B. So once again, there will be 4 ways to do this. We have 3 of one thing and 1 of another. And then if we had all B's, there's only 1 way to do that. Well, we could express the same thing in terms of combinations, right? We could have said that this was the combination of 4 things where we selected 4 of the 4, right? And you can quickly compute that that is in fact 1. This is the combination of 4 things where we chose 3, because we chose 3 of them to be A. So that ends up being 4 factorial over 3 factorial, 1 factorial, which does in fact turn out to be 4. And then this is the combination of 4 things where you selected 2. And by selecting 2 A's, it means you didn't select 2 B's. I'm sorry, that means you also selected 2 B's. So you had 4 factorial, you have to divide by the number of A's you have, and you have to divide by the number of B's that you have. And this does in fact give you 6. And this would be the combination of 4 things taken, let's see, 1 at a time, which ends up being the same as taking 3 of them. So that's a 4. And this is the combination of having 4 things and taking none of them. There were no A's selected, and that in fact gives you 1 again. So those line up with the coefficients that we would have had if we were in Pascal's triangle here. Okay, so we can regenerate the coefficients for any row using the idea of combinations. All right, so let's answer a question. What are the first 4 terms of A plus B? Let's go to the 10th power. Okay, we could keep going with Pascal's triangle, but we could just write out that A plus B to the 10th will first of all equal the combination of 10 things taken 10 at a time times A to the 10th plus the combination of 10 things taken 9 at a time, because we're going to have 9 A's and 1 B, plus the combination of 10 things taken 8 at a time with 8 A's and 2 B's. And then I'll come down here, plus the combination of 10 things selected as 7 at a time with 7 A's and 3 B's, and then we could keep on going. So if we just needed to know what the first couple of terms were, it would be very efficient using combinations to figure those out rather than writing out all of Pascal's triangle. Okay, I think I'll stop there in this video.